Okay, hello everyone. So welcome to the middle session. So in this session, our first speaker is Professor Sankar from Shaha Institute of Nuclear Physics in Kolkata. And he's going to speak about effects of vector magnetic field on electromagnetically induced transparency with linear pump probe, perpendicular pump probe polarization, right? So I don't know if I said
I
it
can
correctly.
explain that.
So,
Yeah, so yes, thank you, Sourav, Saikat, and Bimalendu for giving me the opportunity to see you all in person. I always use this word as in person, but sort of like it should be told that this is the normal thing that we expect to be having, and not online, but yeah, that was what we had for the last 2 years. So yes, I will be talking about magnetic field, vector magnetic field effects, which is based on electromagnetically induced transparency, and what she meant by linear perpendicular linear polarization, that is the pump and the probe, both are linear polarized, but they are mutually orthogonal to each other. So that is what it means. So this is the paper that has been published, and the work is based on this paper also. The talk is based on this paper only. So we start by the selection rules of angular momentum, which you all have studied during your MSc. So it says like if you have a light polarization and if the magnetic field, that is your quantization axis, and the electric field, they are perpendicular to each other, then in the Zeeman splitting, you only see the sigma lines. That is, the selection rules of delta m plus minus 1 will be observed in the absorption. That is when the E and the B are perpendicular to each other. And we also know that if the E and the B are parallel to each other, then delta m is equal to 0 transition will be observed, and that is, if you see in the absorbed line, these are called the pi lines. So pi and sigma lines, this comes from the selection rules of the angular momentum. Now, here what we want to do is that if I change the quantization axis, so I change the B to some other value from the propagation direction. So if there is now the electric field and the magnetic field makes an angle between them, and therefore in this condition, what happens is that the electric field has there is a component of the magnetic field or the quantization axis happens, and therefore both the sigma and pi polarization components are need to be calculated. So we have all the transitions possible when we move the magnetic field from the propagation direction. So here the z-axis is the reference frame, which is rotated by theta along the quant. So theta is the quantization axis, and therefore the component E cos theta and pi components come for the E sin theta. Now this is when we rotate the quantization axis by an angle theta. Now things become quite more complicated if we also rotate the polarization axis. That means if we rotate the electric field vectors from the, say, so we started with an XYZ coordinate system where initially the B was along Z, but that has moved to an angle theta. And now we have also rotated the electric field, which was along X. Now we have an arbitrary direction. So under these conditions, we had to go for the rotated coordinate system, which is known as XZ, YZ, and Z dash, X dash, Y dash, and Z dash. So what we want to do is that we want to control the amplitude of these absorption peaks by controlling the effective polarization. So in this case, obviously all the transitions will take place, but we will see that the intensities will not be the same. And how does it change is the interesting fact. So here the electric field that you see here depends upon the phi, that is the polarization axis, as well as the quantization axis, that is theta. So here what we really want to find out and look at it is that what happens when an arbitrary polarized light will be absorbed in an atomic medium in presence of an arbitrary magnetic field. So just make both of them arbitrary and see what is the effect of the transitions, or what is the effect on the absorptions that we know from our MSc days. So how to do that? Before doing that, actually we want to use a phenomena which is called electromagnetically induced transparency. It is sort of like in simple way is that if you have one excited state and two ground state. So if I have a laser and I shine the laser from one of the ground state to the excited state, I get an absorption profile that you all know. And then this is the dispersion profile that you get. And now if I come with another laser from another ground state to the excited state, then what happens is that the absorption profile is splitted. Actually, you have a transparency in between the absorption profile. So this is sort of a coherent nonlinear optical nonlinearity, which makes the transparent medium transparent in a narrow spectral range in the absorption profile. So this is how it looks like. So this is some sort of velocity VSOP, velocity selective optical pumping absorption profiles. And then at one of them, we got this sort of an EIT. So you see that EIT is a very sensitive kind of detection method. And yes, and we also got something like an EIA, but that is not what I'm going to talk about. And this we call as a lambda system. So you see that there is two ground state, one excited. So this forms a lambda type of system. Okay, and the frequency difference of the two beams is equal to the separation of the ground state. That is one of the requirements to get this EIT working. So what we did here is that so there are two things that we are talking about. We are talking about the magnetic field transitions of the magnetic quantum numbers in the Zeeman, and as well as we are also talking about EIT. So can we match both of them together and see what happens? So what we have talked about, one thing is that we are trying to change arbitrary magnetic field quantization axis. We are trying to change the polarization axis. So both of them, and then we want to form an EIT. So how to do that? This is the rotated coordinate system that I have shown before. So we do that in two ways. First of all is that how to make the EIT. So what we do is that this is the energy level diagram of 87 rubidium D2 transition, which is in lambda configuration. So the pump laser, which is locked from F is equal to 2 to F prime is equal to 2, and the probe laser is scanned from F is equal to 1 to F prime is equal to 2. And this is the excited state, and these are the two ground states. So this is the way that we form the lambda EIT system. And now the other thing is that how would you change the quantization axis? So this is the pump, and this is the probe laser. So what actually means is that by using this half wave plate PBS, that is polarization beam splitting cube, and another half wave plate, what we do is that we mix them together, and it maintains perpendicular linear polarization conditions. That means the pump has a linear polarization, the probe has a linear polarization, but they are perpendicular to each other. So so what happens is that when I mix them two, and this wave plate, what it does is that it changes both, keeping them perpendicular. Okay. And now this is the case of polarization axis. Now, how would you change the B, that is the quantization axis? So we have a Helmholtz coil, which changes the transverse magnetic field, and a solenoid which changes the longitudinal magnetic field. And if you change the current between the two, then you get the direction of the resultant magnetic field. So if you put 1 0 and change the other one, or have a combination of them, then you can change the resultant magnetic field. So this is how we do the experiment. Now, what happens when we do that? As I have told you that when we have such kind of a complicated system where we have a quantization axis and the polarization axis at an arbitrary direction, the electric field has all the components of sigma and pi. So it forms these sort of like really complicated Zeeman level splitting. And then this is the picture, what you get here, and there both the probe and the pump has sigma plus minus and pi components. So they can couple to delta M 0 and plus minus 1 transition. So if you see in the picture, then this is the energy level diagram, and the blue, red, and green ones are for the sigma plus, sigma minus, and pi transitions. And this is the zero energy level. And when you put the magnetic field, you see that there is a shift of the energy due to the magnetic field that you have put, which the shift actually depends upon this value. So it depends upon the B and Bohr magnetron F factor, Landry factor, and other things. So this is quite a complicated system. So during our experiment, what happened is that we were doing this, and there was so many spectrum coming that it was almost impossible to understand what we are doing and what not. So we want to break these things up. So how does the spectrum looks like if you have such a complicated setup? So this is the spectrum. How does it look like? So these are, so remember one thing, that at every point, we are actually forming an EIT. This we have to always keep in the mind, that these we are forming an EIT means this is pump. So you can see like this is pump and this is probe, or this is pump and this is probe. But keeping in mind that my selection rules has to be always obeyed. And then we can have a pump and probe addressing different levels. And if you address the different levels, you will get the shift in the energy, and then what you get a spectrum is like this. So this is the probe transmission. So let me tell you another thing is that we are only detecting the probe. Okay, so one of the ways why we are keeping these two perpendicular, like pump and the probe perpendicular, is that at the end of the day, we can only detect the probe. So it's a very cleaner spectrum. And so what happens is that this is the probe spectrum, and in the probe spectrum, all these tiny peaks are actually EITs, all of them, because there's from one EIT when you don't have a Zeeman splitting of the hyperfine levels, and there are many EITs when you have so many splitting due to the different allowed transitions of the Zeeman levels of the hyperfine levels. So how we got this is that we got this keeping the quantization axis theta at 45 degree and the phi, that is the polarization axis, as 40 degrees. So we put both of them a little arbitrary. So just from, this is the propagation direction, so the quantization axis as 45 degree, and being both as perpendicular to like this, both as perpendicular, now we have turned it to 40 degrees. So if you have both like arbitrary this sort of numbers, then what you get is that you get pi EIT peaks and, sorry? This is arbitrary. Actually, I mean, this is for 45, there is 44.8. So we measured the current between the longitudinal field and the transverse field. I mean, measured the magnetic field, and then we calculated the resultant magnetic field, sort of like that. But the polarization you can choose by half-wave pair. Yes.
Is static at a particular detuning,
yes,
right? Is it not possible to make oscillating between two detuning, like a time dependent delta is a fixed, right? So that you can have a tunability more
by changing the magnetic field,
by
or we can.
You can do it.
We can. This is one characteristic spectrum. I will show you at the end that there are limitations of many things like that. Depending upon what is the range that we can go for.
Means I mean that dynamically shifting the EIT transparency window throughout the means time scale.
Yeah, it's possible.
It's possible.
Yeah.
So what to do then in that case?
Changing the magnetic field, I would say.
Changing the magnetic field, it will give you only the hyperfine separation or the population redistribution among the ground state. But it will not change the center of the EIT tip. Frequency modulation, thank you. Not amplitude modulation, frequency modulation can do it. Thank you. Thank you, Melinda.
Okay, you mean to see changing the detuning and things like that. Okay, fine. Thank you. Okay, so how to identify these seven transitions, 7 EIT peaks from a complicated picture like that? So what we did is that we actually broke the picture into in a simplistic way, so that we first tried to find out that since the electric field, due to this arbitrary direction, has all the components of lambda, of sigma and pi, therefore these are the 4 pictures. So you can see like A, B, C, D. The A is pump and probe both as sigma polarized, probe is pi polarized and the pump is sigma polarized over here. Here it is the opposite. The pump is pi polarized and probe is sigma polarized, and here both of them are pi polarized. So you break up the picture, and then you can see that whatever be the shift of the energy, and that you can calculate, and that related directly to the peak. So if you have both pi polarized, it is A0 and A plus minus 2 peaks, which is the sigma peaks. And if you have 1 pi and 1 sigma, then you get plus minus delta, plus minus 3 delta sort of things. And if you have completely pi polarized light, then you have only 2 peaks of plus minus 2 delta. So here, and keeping in mind that there are many possibilities, but delta, these transitions are always has to keep in mind. And this is sort of a gamut of a lot of EIT possibilities that is happening there. And therefore, it gives this sort of a spectrum. So it was good that we could understand at least qualitatively. Now what we did is that after doing this, you can do something more. So this is at a particular polarization axis and a particular, say, 45 theta and phi. But then you can obviously change the theta and phi to change your quantization axis as well as change your polarization axis. So what we did is that we first tried to do a probe transmission with quantization axis variation. So we kept phi is equal to 0. So therefore, the probe is actually in the direction of in the x direction. So it is in the plane. And then we tried to change the b. The video will not run. I will run. So I will run to make this run. Yeah. So what we did is that we changed this quantization axis by changing the. So we increase the transverse magnetic field, keeping the axial field constant. And then what we get is that, see, at the beginning, the theta is 0. So therefore, the B field is along this axis. And therefore, we only got the sigma peaks. So here you can see at theta is equal to 0, only sigma EIT peaks are observed. Okay. And then when I change this effective, when I change the resultant B field, that is when I change the quantization axis from theta is equal to 0 to theta close to 90, then you can see at close to 90, what happens is that over here, we had the sigma transition because electric field was perpendicular. But over here, the electric field and the magnetic field both are in the same direction. So at theta close to 90, we will only get the pi EIT peaks. So you can see here that these are the 3 sigma EIT peaks. But here at theta close to 90, these are the pi EIT peaks. We didn't go exactly at to 90 just because of some conditions of our, say, experimental practical conditions. We didn't go there. So we couldn't go there basically. So you see that from the 3 sigma EIT peaks, we can go to the pi EIT peaks. And and in between them, you can, for any arbitrary direction of the magnetic field, you can see that from sigma, the pi peaks are coming out at some point of time. Then the pi peaks are growing more. And then over here, actually you can only get the pi peaks, but not the sigma peaks. So you can see here that this is A is equal to 0. So all these 7 peaks are nothing but these guys. Okay. I just subtracted a background and I plotted them. And that's not a background, by the way, that's a Doppler. So, and we got these 3, these are the sigma peaks. So you see, this is the A0, and these 2 are the A0 plus minus A. So you remember here that what we get is that the sigma peaks are A0 and A plus minus 2. So here, this is A0 and this is A plus minus 2. So you see that if in between the A plus minus 2, there is something growing up over here and at the edges. These are the pi peaks, that is delta plus minus 1 and delta plus minus 1, delta plus minus 3. And then at 90 degree, you see that this is the central peak of A0, which is getting lower and lower in the amplitude. And these are the pi peaks, which is growing up. So here there was none, but now it grew up, So you see that there is a change of the ratio. If I take the ratio of the A0 peak, and so this is sigma A0, this is A plus 1 or minus 1. And you can see that the A0 peak is going down, but the A1 peak is growing up. And so there is a change of the intensity of the ratio, And obviously, these peaks are getting separated because you are increasing the magnetic field. So there is two things happening over here. Now, this is when I have the polarization axis at phi is equal to 0. Now, if I now change the keeping the quantization axis, that is beta at theta is equal to 90 degree, I now change the polarization axis. So if I change, now what I'm doing is that I'm changing, now what I'm doing is that I'm now changing the phi, but not theta. So theta is maintained at 90 degree. And then what you see is that at theta is equal to 90 degree, when phi is equal to 0, then we only have the pi peaks because the electric field and the magnetic field are all parallel. So we only have the pi peaks. Again, at theta is equal to 90 degree, what happens is that EP is perpendicular, but EC again is along the propagation axis. So we also get the pi peak. In between, what would happen is that we are getting these in between since the quantization axis is, the magnetic field is not changing, therefore the separation is always the same. But between the pi peaks, now the sigma peaks are coming up. And sigma peaks came up, and then at phi is equal to 90 degree, there is no sigma peak. At phi is equal to 0, no, there are no sigma peaks. And in between, in the arbitrary polarization angle, we get the 7 EIT peaks, as you can see here. So sigma peaks are coming up and then diminishing as we are changing the polarization axis. So we try to understand this phenomena, and then what we try to do is that we try to first work on a theoretical model. So this is sort of a Louis-Valli's equation, in the master equation, you can say, and then we worked out the Hamiltonian for that. And yes. Can I ask? Sure.
I see also a very interesting line shape, especially if you see at 0 degree, that black one, right? Okay. So you do see an asymmetric line shape for the, and which is kind of symmetric. Do you have an explanation for the EIT line shape? If you look at the...
No, really. Huh? I mean,
no, that's very nice.
Thanks for observing,
actually.
But okay, we didn't look at the line shapes here.
Okay.
Okay.
No, that looks something interesting.
So, So, is that a region where the pump and probe, they are both away from resonance?
Which one?
The asymmetric line shape thing.
No. These are the transitions due to plus 3 delta, plus minus 3 delta. It's the farthest peaks. So it might happen that since there is a Doppler background, maybe the line shapes are, I mean, you shouldn't believe this one because we just subtracted that, not really in a, you can say in a very experimental way, but it's like hand subtraction sort of. So the line shape may have come because, you know, the actual, how they look like is this one. So these are the furthest peaks over here. So I won't comment too much.
Sankar, I have a related question.
Yes.
So these line widths are several megahertz, what you observed here. But typically for EIT, these are actually very narrow line width, what is observed, because it's a 2-photon Raman transition. So practically speaking, it should be limited by line width of the laser. So how you are getting...
Line width of the laser is something, our laser line widths are 1 megahertz sort of.
1 megahertz?
Yeah, 1 megahertz, maybe a little bit less than that. But
yeah,
and the separations are 4.2 megahertz, 4.1
like
megahertz.
Almost 5 megahertz or something, maybe more even.
Sorry? I will come to the last slide. Yeah. This is room temperature without any buffer gas and no paraffin coated or things like that.
Exchange and everything going on. So that will broaden your line.
There are broadening.
So you will not get the...
And also there is no phase locking of the laser. Power broadening is.
In hot atoms, I think the line width depends on the transit time relaxation.
Yes, yes,
So
yes.
I'm not
But
so
we,
much
those things, I mean, this is sort of a very initial, the first experiment you can see.
beyond the laser line width. I think it depends on the transit time relaxation, because when you change the probe diameter as a function of that, these the widths actually change.
Okay, this probe diameter, both the beams were like 2 millimeter.
So but
Yeah,
you
very
can
small.
vary that, and you
Yes,
can actually
yes.
also
Okay,
vary
okay.
the probe with respect to the pump. So there are different things that you can do, but let's say you can go from like both having the same diameter, but go from a smaller diameter to a higher diameter. So the transit time will be more, and therefore the rate will be less. And
Okay, that is good.
yeah.
I will remember the suggestion.
So
Okay, that's good.
Sankar, just a clarification. So did you use two different laser source for
Yes,
pump?
yes.
Okay. So then these lasers are from optical lasers, or where are they?
Optical lasers.
Uh-huh.
DL100.
So then if, so what is the typical line width they quote?
See, these.
So then if two lasers, then it would be twice, because these are two independent sources. So roughly 500 kilohertz. And your transit time would be depend on the beam size. What kind of beam size you use?
2 millimeter.
Eh?
2 millimeters.
2 millimeter will give you less than definitely 200 kilohertz, I think. 2 millimeter would be roughly 100 kilohertz or less. These are room temperature.
Yeah.
Yeah.
These
So
are
I
room
think it is
temperature.
at the end for 4 to 500 kilohertz. That will be limit. And then if it is few megahertz, then it is the Ravi frequency of the light you are using that may be playing a role.
Ravi frequency was, I don't remember exactly. Intensity, I remember it was, like the pump was sort of less than 1 microwatt, and this was, the probe was, or the opposite one. I will tell you. I have the paper, so I can tell you. Okay. So we did theoretical modeling calculations. So yes, and considered the total Hamiltonian, which is the unperturbed Hamiltonian, light atom interaction, and magnetic atom in Hamiltonian. So it's like Bankim did real rigorous calculation here. Sometimes you feel like your student becomes even more smarter than you. This is one example. Go to the paper. Don't ask me to explain everything because I will do it. But I give the credit to my student. So yes, at the end of all this, I mean, after the numerical simulation, we got this this is the experimental spectrum, and this is the numerical simulation that we got. So we kept the same values for the experiment and this simulation, and density matrix equation we solved actually the 13 level system in steady state condition. So it's sort of like 169 sort of equations. And we took the help of atomic density matrix package to use this simulation. This is almost crazy. So somebody has developed this one, which is thankful, I would say. So yes, we can match our experimental spectrum with numerical, but then we wanted to do an analytical solution to that. So we took a toy model. So what we did is that this is the energy level diagram of the toy model. So we didn't take the entire spectrum, but we took a small section of that so that we can at least get the A0 and A plus minus 1. So 1 sigma and 2 pi peaks. And we assume the same numbers as the experimental conditions. And this you can see that they are considered. And we can, from the toy model, we can get the feature. It's not exact, but we can get the feature. And using that feature, what we did is that now from the solution, we found out the susceptibility. And it took really quite a complicated form. And where these are the Ravi frequency of the ground state and energy states, the dipole moment, the relaxation parameter, probe electric field, Doppler width. So during this analytical solution, we also took care of the Doppler width because the atoms are at room temperature. So Maxwell-Boltzmann velocity distribution has to be taken care, and this is the detuning. So when we do that, what we got is that we got this probe transmission spectra and the for phi is equal to 0, and then the variation of polarization axis for theta is equal to 90. So these things, the analytical solution actually showed the same kind of features that we saw in the experiment. So we had we put some confidence in what we have doing. And here we have in both the figures, the 2 photon absorption is subtracted from 1 photon Doppler absorption to get these peaks. Now the important thing is that can we do a determination of the magnetic field magnitude? So that is what it means is that can we so from the separation of the peaks that we got here, so you can see here that we got the separation of the peaks. So from the separation of the peaks, obviously you can put your formula and then very simply you can get to the magnetic field. And there is a nonlinear behavior at the very low magnetic fields. So we only consider the linear part. There are issues because you have to see the EIT peaks. Therefore, I cannot really have zero longitudinal field and then see it's a resultant field that we are changing. So here has to be, oh, sorry. Okay, so so there is an issue for that because we have to see the EIT peaks. And then we also determine the direction of the magnetic field. So it's very simple. If you can derive this formula from this analytical expression at phi is equal to 0, and then you can get the other peaks at phi is equal to 90 and the other values. So what happens is that these are the experimental data and this is the simulation. So what happens, what the analytical solution tells us that obviously we have taken a toy model, so everything should not match with the other. But yes, from when we have this sort of analytical distribution and we want to know about an arbitrary magnetic field, what might happen is that just think of a device which just scans the polarization axis, okay, keeping it perpendicular to each other, and then these curves will define. And now if you get to know about one magnetic field, if you measure a value, then you can actually put that value and you can map the value to one of the curves. Because if you change the phi, then that same magnetic field will be matched into different sort of A +1 to A0. So yeah, I forgot that. That is because the ratio between the two peaks, because there is a change of the ratio between A0 and A1 peak. So that is the ratio what we are looking for. And then we can get this direction of the magnetic field. And then again, the other thing that you can see here that we also for quantization when theta is equal to 90, then you see that there are also an oscillatory behavior of say A0 peak. So that oscillatory behavior we can also find from this analytical expression. And this, what it means is that at phi is equal to this n pi by 2, you will always get a 0. So there is a maximum and minimum at one value of phi. So this is at theta is equal to 90, we got the A0 amplitude changing like maximum and minimum. So at an arbitrary theta, we will have a shift of this minima and maxima, and that might give the measurement of the direction of the magnetic field. So this is just the locus of A0 peak. And I won't go in the summary that you can always, you can fall back. And what we are heading for is, we are trying to build up this atomic magnetometers in the spin exchange relaxation free regime. I do not know too much about it, but yes, that exploits the utility of buffer gas filled cell, paraffin coated cell, and also heating to atomic density. And we will do that with the polarimetric technique, which we already developed. Utilize of phase lock laser systems will give us obviously better EIT because everything depends on EIT. And then miniaturization of the entire thing may lead to sometime a sensitivity of this. This is not my sensitivity. You see that this is just a first work, so a lot of work has to be done. So I'm not quoting any numbers. I'm far away from actually anything that these numbers can tell. So thank you all. And yes, there are opportunities for Chanakya postdoctoral fellowship. So do ask your PhD students to apply. I have only one PhD student existing, that is Priyobroto, who is in the audience. So do ask your junior want to do this work to apply as PhD students, and do ask your PhD students who are going out that there is opportunity.
Okay.
So thank you.
Thank you. So